Welcome back everyone to the lecture about applied bioimage analysis. This part will be about writing pythonic code. And it is basically like something like 5 weeks ago. It is basically just an introduction of how to write good code and how to avoid typical problems, especially young developers when writing their first Python programs or programs in general have how to avoid these situations. So when you go through my Jupyter notebooks I provided for this lesson, you will see maybe that in different notebooks, like for example testing the curation time of patients and testing the tomato ripen time, I have the same function twice. So I'm basically copy pasting from one notebook to another code. If I do this for this one lecture and I copy over this one function, that might be okay. But if you work for something like 5 years in the lab and you copy paste function from notebook to notebook, you will go crazy at some point. Because first of all, it's becoming more and more functions, and second of all, at some point, you will start modifying them when copying to the new notebook. And then there was this, something like 2 years ago, there was this one modification of this function which was super cool. In which notebook is it again? So you will get lost when you work like that. And that's why I'm strongly recommending you to not copy paste functions from notebook to notebook. Instead, you should build libraries for stuff which you like to use more often. So here's a very simple way of doing that. And it shows you how you combine Python files with Jupyter notebooks. This is why I introduced you at the very beginning to the command line to text editor to PyCharm to Python. And then I showed you Jupyter notebooks because actually if you know both, you achieve the most. So let's assume we have a math library. We developed our own math library which has functions for adding numbers and for subtracting numbers. So this is a simple case, right? In fact, the library could be an image processing library doing awesome stuff, complicated algorithms. I've just chosen this example here to show it in a simple context. So we have a Python file on disk. It's called math library, and in the math library we defined two functions, the add function and the subtract function, which takes parameters and runs some algorithm of that. And then from a Jupyter notebook, for example, you can say import math library if the Jupyter notebook and the Python file are located in the same folder. And then you can, for example, take two variables x and y, hand it over to math library.add, which is the add function in the math library.python file, and execute these operations. So, and there's an alternative to that. You can also say from the math library, I would like to import the subtract method, and then you call the subtract method by handing over the parameters, and you can print out results like that. So the idea here is you take functionality which you use more often between different projects, you put them in a Python file, you maintain it in the Python file, and then you do not copy paste it over anymore between Jupyter notebooks. You always use the same function from different Jupyter notebooks. That's the idea here. You have to code only once, so you don't have to copy paste stuff. This also helps you, I mean, same situation again. If you have a repetitive code, like here in this case, I have twice, it's in one of my notebooks, I have it. And I'm plotting the curation time of the patients receiving treatment and the curation time of the patients receiving the placebo. So these two diagrams should look the same because I would like to compare just different numbers shown in the same diagram. So I have to code twice. And if I change one diagram, I have to change the other diagram as well. And it's like I have duplication of code, and it makes my life complicated. The alternative to that is again in, for example, PyCharm here in this case, I have my function draw curation time histogram. Inside there's all the code which is necessary for that. It has some parameters, for example, data and description, and then I can also call this function from my Python file. You have done this earlier, calling a function in a Python file from the same Python file when executing this program. I can call it from with some test data in this Python file, develop this function until it works as I want to have it, right? And then when I'm done with that, I just call this function from the Jupyter notebook. That is actually very practical when it comes to have more complicated functionality and keep it out of the Jupyter notebook. The Jupyter notebook should be an easy to read overview document where you describe a bit what you're doing, then you're calling a function, you show a plot, and then you describe the next step. So this is how it's supposed to be. If you want to get rid of complicated functionality out of the Jupyter notebook, put it in a Python file. One more hint, If you want to develop the Python file in parallel while also developing the Jupyter Notebook, you have to put these 3 code lines in your Jupyter Notebook, which makes the Jupyter software reload the Python file in the background. Otherwise, it would just load this function once, and then when you change the function, Jupyter does not realize that you changed this function. That's why these lines are important here. Furthermore, documenting code. I mean, if we would now be in a lecture hall, we would go through this function and we would read step by step what it's doing. And I put some comments here. These comments make it easy to read it. So if I wouldn't have these comments here, you may have a hard time figuring out, for example, what filters.gaussian image 5 is doing. And that's why I have these comments here, and it makes it easy to read. So I'm loading an image, I apply a Gaussian blur, I threshold this image, I run connected components, and I analyze the objects, the labeled objects in my original image. And then by the end, I return the number of labeled objects. So how many cells are there in this image? So this is basically what this function is doing, and the comment would be helpful for doing that. And you later on should be able to read code like this and to roughly say what it's doing step by step, but also in general. And you can in Python, it's something new in Python, which you cannot do in image macro, for example. You can have default values for variables, for parameters of functions. And so you say here, for example, threshold equals none. And if you can then later in your code determine if threshold is none, you can automatically determine a threshold. So either the user of your function hands over a threshold for thresholding the image, or if it does not, then this threshold is determined. So from a Jupyter Notebook, it looks then like that. I call the analyze image function, which is written here, and I hand over obviously a file name and the number 2. So what is this? What does this 2 mean? If I don't see this Python file, if I only sit in front of a Jupyter Notebook and I read this 2 here, it might not be very helpful. That's why I would recommend you write down the parameter name here. So this is what you can do in Python, but you can unfortunately not do in many other programming languages. But it's helpful for reading this piece of code. So this is something like a comment, but makes your code easier to read. Second of all, comments, or in Python there's a concept called docstring. You can, inside your function, you start with these 3 quotation symbols and then you document your function and what this function is doing. If you really stick to this particular way of formatting it or not is a decision for you, but I can recommend you because it has some beauty. So I first write in a sentence, what is this function doing? This function loads an image, blurs it a bit, and applies a threshold. And then what parameters does this function have? So there's a file name parameter, image file to open and analyze. There's a Gaussian blur sigma, and that's the sigma which is handed over to the Gaussian blur function to blur the image a bit in order to get a smoother segmentation out. And we can also hand over a threshold. So this is what this block here says. It documents all the parameters this function takes, and it does that in a certain format. Furthermore, this function returns the number of objects in the image after thresholding, after applying this Gaussian blur. And it is a long piece of text and a lot of blah blah, and it may be, in this case, in a function which has something like 10 lines of code, it may be trivial and you are too lazy to write that. But if this function becomes longer and does sophisticated stuff, you may really want to write that stuff down, also because of this. And so assume you have written this function a year ago, and you now want to know, what is this function doing again? What did I think a year back when I wrote this function? And because this so-called docstring is here, the documentation is in the function, you can, from a Jupyter Notebook, for example, say print analyze image dot underscore underscore dot doc underscore underscore, and it will print this thing out. So you can read the documentation of your function from a Jupyter Notebook, from somewhere else. And alternatively, in PyCharm, for example, you can, with your cursor, you go on the function and you press Control Q, or on Mac, I would assume Command Q, and this window pops up, which tells you the same story. So you have, this is how you can build in documentation into your function so that later somebody else or yourself can read that. Very helpful if you maintain a lot of code, if you run projects with a significant amount of Python code. there is in Python, there is a couple of concepts which are thought of for simplifying code or for writing code in a way how it's more convenient. So this is basically something you have used already last week. We have we start with an empty array. We have a for loop going over a certain collection. We check if for every item in this collection some condition is fulfilled, and if yes, we add to our values, we add a new entry. So for example, we go over a folder, we check if the file name ends with TIFF, we analyze this image, and we put the result of the analysis in an array. So this is what you did earlier. There is an alternative in Python you can also write, and so that this becomes a little bit easier to read. You can also say values equals an expression, so we do something with the image, we do something with an item for an item in the collection in case the condition of the item is fulfilled. So it's kind of, instead of saying we go through this and we check that and then we do it, you say we do it while going through it, checking it. It's the other way around, which only works in Python. Some people love it, some people hate it. And I wanted to show you that this thing exists. So this is the rough explanation how in general it works. And here you see a practical example. So assume we have a collection, a list of numbers, and we can now go through this list of numbers with a for loop, and we can multiply these numbers with 2 and put the result into the output and then print out the output array. So all the elements in this array are multiplied entities of the array elements from the input, and you can write it the other way around. And here you may agree, oh, it's so short, it's doing the same. It is indeed, because we say the output equals the value times 2 for every value in input. That's a lot shorter, that's easier to read, I agree. And you can also do image analysis with that. So assume we have a function process image, or like the function analyze image I introduced some slides earlier. We can either go through, we have a variable directory, we have a file list, an array containing all the files in this directory. We can go through the file list. We can check if the file ends with TIFF, and then we can, if this is true, process the file name, or alternatively, we can process the file name for all file names in the list in case the file name ends with TIFF. So it's like, this is the same, these two code snippets do the same, but they are completely different to read, completely different to write. So this is an opportunity you have in Python in order to shorten your code, in order to make it easier to read and understand. You just have to be familiar with this concept, and that's why I'm introducing you to this concept. There's one more thing that brings us to object-oriented programming. I just wanted to show you. But let's assume we have two functions, and one function computes the area of an ellipse, and the other function computes the aspect ratio of an ellipse, and both functions take the same parameters. So we have a minor axis and a major axis, and we can, in one case we compute the area, in the other case we compute the aspect ratio. And we have these functions, we call them from time to time. We have to hand over the same parameters again and again. This is how the execution then looks like. We have a minor axis and a major axis, and call the function area of ellipse and aspect ratio of ellipse with the same parameters. So you have to hand over the same parameters over and over, and you should also not mix them up. So major or minor, you have to know, you have to hand over the right one, otherwise the results, especially in case of the aspect ratio, may be wrong. In order to, it is a form of simplification, even though it looks a little bit more complicated at the very beginning. We can also define a class, which is an abstract representation of the object ellipse. So we can define an ellipse, and an ellipse has initialization parameters. It has a minor axis and a major axis. What I do here, there's a third parameter, it's the so-called self parameter. If you programmed earlier in other programming languages and you know what this object is, this and self is basically the same concept. So the self object represents the ellipse. And when we initialize a new ellipse with a minor axis and a major axis, it's nothing else like storing these two values, minor axis and major axis, in the self object. So self minor and self major become minor and major. So we just initialize a self, an ellipse, with these two numbers. And then afterwards, when we call, for example, area on the ellipse class, it only takes the self and can from self minor and self major compute the area and compute the aspect ratio. So this part looks a little bit more complicated, I agree, but when you call it, so from the user's perspective who just wants to use these functions, it's simpler because you can actually say, okay, I want to have a new ellipse with this minor and major axis, and then from this ellipse I take the area and the aspect ratio. And please note, the self is not handed over here, so it's not written. It just exists in the class definition because we need it as a representation of the one ellipse we are talking about. In the code later on, you have a variable e1, which corresponds to the ellipse, and from this ellipse we can ask for area and aspect ratio. You may now see here in this code, when you think about feature extraction some weeks ago, the aspect ratio is actually supposed to be larger than 1. And when I print out here the aspect ratio, it's 0.5. That has something to do with the fact that I entered these two parameters here, the minor and the major axis, in the wrong order. So that's my user's fault, and you can catch users' faults in these class definitions. So when I have this initializer here, basically it's the same code, just this here is a little bit different. If I realize, or if I check that the minor axis is indeed smaller than the major axis, so this is what minor and major are about, right? Then I save them as they are. So for example, save.minor axis equals minor axis. If I realize that the user handed it over in the wrong way, I can spit out an error message and warn the user, or I can deal with that here at that level by saying the major axis equals the handed over minor axis, and the minor axis equals the major axis. And then suddenly, even though I entered these two numbers here in the wrong way, the aspect ratio is correct. And you don't have to do this check or this spitting out an error message in every individual function. You do this once in the initializer of the class. And I'm introducing here to the concept of object-oriented programming, not because I want you to do this. It's really like it's a little bit an excursion, let's say. But if you like this idea, if you like this concept of what we are doing here, we have an abstract representation of an ellipse, of a tomato, of a patient, and then we do things with the ellipse. We get the area from the ellipse, or we grow the tomato or something like that. We make it ripen. If you like this concept of programming stuff like that, and you are now doing a bachelor in biomolecular engineering, you might consider studying a master afterwards in bioinformatics, because stuff like that and having objects and pushing them around is a typical computer science thing. If you like this concept, consider moving on towards this direction. And if you don't like it, it's absolutely okay. Okay, that brings us to the exercises for today. Please take the exercise from last week. So you were doing method comparison last week, mostly descriptive, actually only descriptive statistics. You were drawing Blunt-Altman plots, and you were looking at the differences between O2 thresholding in ImageJ and in Python. Please take the notebook from last week and the data which is in this notebook, so the two arrays, and apply an equivalence test to it to figure out if these two methods deliver mean values or deliver distributions of values which are the same, which have the same mean coming from the same population. Furthermore, when you go some weeks back, lesson 2 and 3, you will see that we measured the area of the embryos in the embryo image in Fiji. We did it manually, and then in the lesson 3 we did it automatically with the particle analyzer. Later on we even programmed a little macro doing it. Compare these measurements. Do descriptive statistics on these measurements and do hypothesis testing. And I'm not telling you what test you should do, because I would like to ask you to think about what test is the right test to compare the manual and the automated measurement done at the beginning of the semester. If you cannot find the results from the beginning of the semester anymore, there's two ways of dealing with that. Way number one, you train ImageJ again, and you annotate these embryos manually with the ROI manager, and you do a measurement manually with the ROI manager. And afterwards you write a little macro. I think you don't even have to write a macro. You just use thresholding and the particle analyzer to get an automated measurement out. Or alternatively, if you're running out of time, the two tables for a manual measurement and an automated measurement are here in the folder for the exercises. But feel free to refresh your knowledge from the beginning of the semester of how to process an image like that. It is especially necessary to do some thresholding, to do some binary image post-processing. There's a watershed likely which has to be applied to this kind of data. If you want to refresh these things, then just do it again. It can be done in something like less than half an hour for sure. It was a lot. Hypothesis testing is really like, it is a bit a twist in the brain, I know, but I would especially highlight when you derive some random numbers in a Python Jupyter notebook and you apply some t-tests to these random number arrays, you will get a feeling for what you are doing here and why things are happening in this particular way. So I introduced you to a couple of tests, and I also showed you how to use these tests in Python. I was also showing you some advanced Python code. Next week, I would like to return a bit to image analysis. What we skipped during the semester was processing three-dimensional images. So we will do this next week, and we will do it very likely. We will do it in ImageJ, and we will do it in Python with a software Napari. So see you next week.